What we're going to do at this point is I'm going to begin my discussion of C++ generic programming by focusing on class functions, or class templates, and function templates. So let's start by motivating why we even need all this stuff. So C++ is a strongly typed language for the most part. And what that means is you have to declare your variables with their data types before you can use them. And if you get confused and you define something to take an int and you pass it a double, then it should complain at compile time and say, you can't do that. And there are a couple of reasons why this is valuable. One, of course, is that it helps the compiler optimize the storage of the types because it knows how big they are. And then it can also make sure that only the right operations are performed on the types and that it can pick the most efficient ones. Another thing you can do with strong typing is you can do type checking to do things like prevent memory leaks or prevent illegal operations that would spring on you at runtime when your program's in the hands of your customers or your program is controlling the nuclear reactor or whatever, and you're not there to make sure it works properly. So strong typing helps to, shake out a lot of bugs from your code. But there is a downside to strong typing without proper feature combinations in a programming language. So one of the downsides is that if you need to perform the same action on many different types of variables, strong typing can make your code rather tedious. And that's one reason why some languages like, say, JavaScript and Python are weaker in their type checking. They can do they basically allow things to be dynamically checked, or if they're even checked at all. And so that gives you more flexibility, but it comes at a cost of not knowing what your code is going to actually do until it runs, and also just the overhead of trying to support the more dynamic type checking model. So one way to do this with languages like C is to use older mechanisms like the preprocessor in order to make macros and so on that can work with different data types because it's just doing roughly textual substitution. And I'll show you some examples of that later. Another way to do it, which is also popular in languages like C, is to have containers of void pointers, and then the type system is effectively subverted. But these are all kind of hacks, and they have many downsides in terms of performance and in terms of type safety, which is the main problem here. So another way to do it is to use overloaded functions. So we'll see an example of this in a second, but if, let's say you want to have a bunch of functions that will add various data types. You could define a plus method for int, you could define a plus method or plus function for float, a plus function for double, a plus function for long, all the different kinds of things you want to add. You could have a huge spate of overloaded functions for every one of those different data types. But my gosh, is that a pain? It's tedious and error prone to develop. It's tedious and error prone to debug. If you document the code, you have to document things over and over and over again. So it very quickly becomes difficult to maintain or sustain that kind of code. So how do we fix this in C++? Well, as of C++ 2.0, which is now about 30 years old, they define the concept of a function template, which allows you to write one generic function that can be parameterized with what you're actually trying to do the work on. And that's a very powerful concept, and that's what we're going to talk about first. C++, of course, also defines class templates, which groups a bunch of functions, or member functions as they're called, into a cohesive unit, and then allows you to put the parameterization at the top, and then they all sort of inherit, using that word loosely, the types that are being defined, or the type that's being defined in the class template declaration. So we're now going to go on a fairly extensive journey through the space of templates in C++, STL. And this is very important because if you don't understand templates, you will be able to make no sense out of the way that C++ STL actually works. So having this foundation is extremely useful. And of course, it's also useful because not everything you're ever going to do in life with C++ will be based on STL. For example, your programming assignment that you're working on now, your second programming assignment, works with templates, but it doesn't work with STL necessarily, or very little. So as a consequence, it's important to know how to build templates and use templates, even if the ones that come out of the box from STL are available. You may have to do something else that's more specialized for your needs. Okay, so let's go ahead down here and start looking at some examples. So here's our first example. And this is kind of a recapitulation or reiteration of the point I made a little bit earlier. So C++ has long supported overloaded functions, but as I think you probably know, these can be very tedious and error-prone to write, especially if the logic for each function is the same, but only the types differ. So what's an example of this? Well, one example would be plus. So here's a bunch of overloaded functions that take two parameters, add them together, and return the result. And as you can see, we define plus for ints, we define plus for longs, and we define plus for doubles. What a pain. Who the heck wants to write and maintain this code? I didn't even bother documenting it because it's just a throwaway example, but it would just be impenetrably hard to try to manage all this stuff if you had to do it manually like this. So what does C++ do to save us from the duplication of effort? It defines function templates. And these are basically functions that can operate on different data types that are parameterized without having to repeat yourself and duplicate the code. So the nice thing about templates is they support the so-called don't repeat yourself or dry principle of software development. And the dry principle, by the way, is really at the heart of software reuse. You want to be able to reuse the elements without having to rewrite them over and over again in a tedious way. So rather than writing a whole bunch of different overloaded versions of plus, we're going to define one method called add, and then we're going to parameterize it. And you can see here, I think you probably already guessed, this is very simple. We have a template, type name t, and then we define our generic function add, which takes two parameters of type t, adds them together, and returns an element of type t. And later we'll return and we'll talk about other ways of doing things. I'm keeping it very simple right now. So let's take a look at an example here that compares and contrasts the use of the non-template functions that are overloaded with the template functions that are not overloaded but are synthesized by the compiler from one generic function. So we're going to define a bunch of data types. We have ints and longs and doubles. And I probably, if I was really being a good citizen of writing code that's going to be more bulletproof, I would do something like this: int, long, double. It's always good to define your types and initialize them when you're doing that. Just has less confusing errors. And you can see here that we're just calling the plus operations that are overloaded, the plus functions. So that all works fine. And if we print this out, we'll get the expected values. Down here, we're doing the same thing, except we're using our generic function add. And you can see we never had to write that more than once. Instead, when we say add for ints, we can put the less than int greater than, add for longs, less than long greater than, add for doubles, less than double greater than symbols. And what that tells the compiler and the linker is to go ahead and automatically synthesize code for add for int, add for long, add for double. And in fact, because of the way that templates work, there may actually be no code at all. This may all just turn into complete inline adds. So one of the great things about STL is the code here may just be as simple as I plus j assigned to k, L plus M assigned to N, and A plus B assigned to D, which is not only much easier to write, because we only had to write the add generic template once, but they may actually be even faster than making the function calls that were overloaded here, because those might be compiled in a different module, and we have to actually make a function call. So we may not only be able to make our productivity increase from a human coding perspective, but the code may be faster. So this is yet another great example of zero overhead abstraction that Bjorn Strustrup likes to talk about with C++. If you make your abstractions optimizable and you choose them wisely, you can actually get performance that outdoes traditional approaches using more, quote, low-level languages like C. So that's pretty cool. So let's go ahead and run this code. Hopefully it'll work. And as you can see here, it does in fact work. And we get the same results using the overloaded plus methods, as well as the same results from using the methods that are based on the synthesized add templates. Okay, so that's our first example. Now that we've looked at our first example of using a generic function template, let's go ahead and take a look at some variants in the way that it's going to be usable. So again, just to recap, here's our simple add function, which takes one parameter, adds the results, adds the two parameters together and returns the results. I think that's pretty clear. What we're going to do now is we're going to show how the C++ compiler can do something known as type deduction. And as you can see here, what it's going to do is it's going to allow us to be able to make the add call while omitting the actual type. So we don't have to say, int here. We can just say add I of j, add L&M, add, in this case, 10.5 and 16.7. We can add in that case, doubles. And the compiler will automatically deduce, aha, this person's calling the add function for ints. I'll synthesize an add function for ints. This person's calling the add function for doubles or the add function for longs. I'll automatically generate the add function for doubles. I'll automatically generate the add function for longs. And as I said before, I can optimize all the overhead of the function calls away by doing the operations in line if it deems that relevant. One thing you should note, though, is with templates, it expects the parameters to match correctly. So in this case, our template only took a single parameter, and therefore both A and B need to be of the same type. So if we try to do this, add IL, where I is int and L is long, the compiler will yell at you and say, there's no matching function call for this because I'm expecting to have both parameters to the add function, both A and B, be of the same type. Now we'll come back and see how to relax that constraint later by adding a second parameter to our template declaration. But for now, just be aware that the compiler expects those things to be the same if there's only one type that's parameterized. And so I think, just for completeness, I'll go ahead and run this, but I think you can imagine it's going to give the right results. And this way, we demonstrated how the compiler can automatically deduce what types are passed in. And this ability to deduce the types figures in very prominently later when we talk about various adapters in STL, like iterator adapters and other types of adapters, because it makes the code a lot cleaner rather than having to put the types in all the time. Be aware, by the way, that you can only have deduction on functions. The compiler won't deduce specific instances of objects that are instantiated with classes or structs, and that will also become a little bit more clear when we get further down the line. Okay, let's see if there's any questions. It does not look like there's any comments, so I will continue. So now what we're going to do is we're going to talk about a couple of other variants of function templates. First, we're going to show how you can have a function template defined that actually uses multiple different type parameters. So here we're going to define a function called max, which is parameterized by type name R, which is the return value, type name T, which is the first parameter, and type name U, which is the second parameter. And as well, second parameter to the max function. And as you'll see, the actual implementation is pretty obvious. The max of A and B is going to be A less than B, question mark, in which case we return B, otherwise we return A. The syntax here, this is what's called the ternary operator. And the reason it's called a ternary operator is there's three parts to it. We have the expression A less than B. We have the question mark, which says, is that true? If so, then we do whatever comes after the question mark. Otherwise, we do whatever comes after the colon. And this code is basically equivalent to if A less than B, return A, else return B. So that code is equivalent. The main difference, of course, is that this code here is an expression, A less than B, question mark, B colon A, and this code down here is a statement. But they both have more or less the same effect in this context. So now that we've gotten past that, you can see that we can decide what we want the type R, the type T, and the type U to be. And let's take a look and see how this works. So what you can do is you can let the compiler deduce certain things, but there's some other stuff that you actually have to tell it. So here's an example where we want to compute the max of 5.5 and 2, and we want the result to be a double. And so what's happening here is the double that we're providing there is actually for type name R, for this guy, and then we're letting the compiler deduce that it should be a double here and an int here. And that turns out to be perfectly fine because we differentiated between type T and type U up here in the template parameter list to the max function. So that all works perfectly fine. You have to provide the return type, though. The compiler won't deduce that for you. And that's a long-running debate in C++ compiler circles, but it doesn't work that way. I think this is probably trying to tell me to use an auto. Let's see what it says. Yep, it wants me to use an auto there. So what the heck, we'll make it an auto. But it's a double. Then down here, we're showing how you can tell it specifically all the different template types to use. So we're going to be finding the max of the character A and the character B, and we're saying make the return value be an int, and then treat the other parameters as characters. And so that's telling it what we need to do. And so if we run this code, you can see that this is going to produce the results that we'd expect. The reason why the max of the character A and the character B is 98 is that little a is got the ASCII value of 97. Just for kicks, let's go ahead and do this just to show the difference. So if I do this and I run it, it should come back with B, which it does. So now it's treating those things as characters and not treating them as ints anymore. Okay, so that's another variant of using templates where you can explicitly tell the compiler, use this return type, use these types of parameters, or you can let it deduce that on your own. And this also shows you that by putting more types here, it gives the compiler more freedom to do conversions and other kinds of things without locking you into the Procrustean bed of just one type, which is what we had done before. All right, let's go on to the next example. And keep in mind, all these examples are available in my my GitHub repository, so you can go and poke around with them and learn from them and modify them at your heart's content. I strongly recommend that you get used to taking the code and playing with it. That's the single best way to learn how this stuff works, is to try it out. You can read books, you can attend lectures, and you'll sort of understand. When you start actually writing the code, it becomes a lot more tangible, and you'll remember it a lot longer. The next topic is talking about the fact that even though we use templates to get around overloading, you can mix and match templates and overloaded functions very nicely. In fact, you can also have basically overloaded class templates as well, as we'll see later. Those are called specialized or partially specialized templates. So we're going to see that we're going to see how this works. We're going to have a generic function here, and then we're going to have some specializations of this function, and then we're going to see which version the compiler picks under different circumstances. And this is really cool. And this again shows you the power of C++ and its type system in order to let the compiler make the appropriate choices when given alternative things to choose from. And this is forming the basis for some more advanced concepts we'll talk about later called template specialization, which is really cool. So here's our generic function. I gave it a very unimaginative name. It's called f for function. And it's parameterized by a single type name T. And rather than doing anything, this function just prints out template. Again, not very creative. Down here, we have an overloaded non-template function. So this function f takes 2 ints. And it, again, doesn't do anything very creative. It just prints out non-template. So we can now differentiate between the template version of something and the non-template version. So let's go ahead and take a look now at some calls here. And if we had voting set up, we could vote on which version you think will call which of the functions. So the first thing we're going to do is we're going to go ahead and call f with 1 and 2, which are ints. Then we're going to go ahead and call f with a and b as characters. And then the third thing we're going to do is we're going to call f with 1 int and 1 character. So, you know, if this was a game show, we would play the theme song to Jeopardy, and you could try to figure out, you know, what's going to happen. And what I will tell you is, because I've run this code many times, this version is going to pick the function that's the int function. This one, the specialized one. This is going to pick the template function. And the reason for that is that there is no specialization of functions for characters. And then this function is going to pick the non-template function. And what it's going to do is it's first going to promote this character b to an int, and then call the one that's the non-template version. So let's go ahead and run this. It should come back with non-template, template, non-template. So we'll see if I remember this correctly. And in fact, that's what it comes back with. So the reason this is doing this is the compiler always prefers the specialization over the generic template. So given a choice between a generic template like this and a specialized function, it'll always pick the specialized function. And that's very important to remember when we talk later about template specialization, because you can mix and match these things and have the compiler pick the right one. There was no version of f overloaded for characters, and since templates don't do type promotion, they always expect exact matches, this will be the template call. And then this version here is not the template version because it has to be an exact match, and there is no template function that is parameterized by 2 different types. It's got to be the same type. So in this case, it goes ahead and it does what's called type promotion. And there's some implicit conversions that are defined at the C level parts of C++, where if you have a character and you're using it in a context where an int is expected, the compiler will implicitly promote the character to an int. And yes, that's confusing, but that's just the way it works. So we have to suck it up and deal with it. By the way, just for kicks, we could have done something like this. We could have said f char, and then let's call this non-template part 2. And when I run this thing, then the middle template should be replaced. Whoops. Oh, now we've got a problem because we have an ambiguity. Let me do this. Let me comment out this code for a moment. And then we'll go ahead and call. And you can see that in that case, calling f with character literals ends up picking the specialization that was this one. I'm going to go ahead and comment this out because you can see it causes problems, because now it's ambiguous which of these things to call. It doesn't know what implementation to use. And whenever there's an ambiguity, the compiler throws up its hands and says, I've got an ambiguity, you figure it out. And of course, there are various ways we could resolve that ambiguity. We could comment it out as we did here. We could have a specialization that took an int and a character, and then that would be selected. So there's lots of different alternatives for dealing with ambiguous type resolution with overloading and templates. Okay, so that's another example illustrating some of the core concepts with templates. This is basically the concept of partial specialization and template explicit specialization. Let's now go ahead and take a look at the next example. So this example kind of summarizes function templates. These are the things we've been talking about so far today. So function templates define a family of functions for different data types. When a program invokes a function template, the arguments that are passed to that function are only instantiated for the data types that are actually used. So this is a really cool optimization. If you have a bunch of function templates that are never instantiated, they're not going to generate any code. So it's an optimization built into C++. So it's kind of like the Liberty Mutual commercial that says, only pay for what you need. There's this insurance company called Liberty Mutual that has all these somewhat whimsical commercials with an emu and a guy named Doug, and it's emu limu, the emu limu, or something like that. And their tagline is only pay for what you need, and that's kind of the way that templates work in C++. The compiler only instantiates stuff that you actually use. As we saw, a program can invoke a function template either by explicitly passing the parameters inside of angle brackets, or it can let the compiler deduce the type if it's going to be unambiguous. You can overload function templates, but do this carefully, and usually you do it in order to provide some kind of a specialization, template specialization, to have the compiler pick the one that's more specialized. When using function templates, make sure the types of arguments you use to invoke the function will work with the given set of function templates. Kind of goes back to the ambiguity problem we were looking at in the last example. And again, the compiler tries to pick the ones that have the more specialized behavior. So here's an example to kind of wrap this up, and this will show a bunch of interesting things as well. It's kind of fun. So here we're going to have some functions called min. So let's go ahead and take a look. Here is the first min function. This is going to take two parameters of type t, and it will go ahead and return the min. This one uses the if syntax, the statement syntax, whereas down here I use the expression syntax. We'll get the same result back in both cases. Here's another min method. This min method takes three parameters, and you can see that the three-parameter min function uses the two-parameter min function to do its work. So it says, to compute the min of P1, P2, and P3, all of which have to be of the same type, it goes ahead and says, is P1 less than P2? And is that less than P3? Then we have to go figure out the min of P1 and P2, and otherwise we return P3. So it's just a little bit of kind of logic, sort of Boolean logic, to figure out what is the min here. And then the third example rather of a generic function is intentionally way over the top. And this is using some super advanced C++ template mechanism that's just completely insane. So this type is going to deduce the return value for min of two different types. So unlike the min we had up here, which only takes one parameter, in this case, we're going to give it type name A and type name B. And then this particular min functions will deduce the type of the return value based on the types that are passed to it. And this, I'm just going to tell you what this does. We're not going to walk through this in any detail, and I'll show you how it works. This uses a very cool feature in C++ STL called decal type. And we've looked at some examples of this in some other contexts if you've been following my C++ STL by example webinar series. So decal type will actually return the concrete type based on an expression or based on some parameter or some variable. So what we're doing here is we're taking a look at the expression a less than b question mark ab, and we're converting that into a type. We're stripping out any reference semantics, and then we're going to define this as the type that will be deduced and used to replace auto. And this funky arrow here is what's used to do right-hand side type synthesis, I guess, for lack of a better term. And so it's another very advanced C++ feature. So what we're doing here is we're basically deciding at compile time, sorry, at template instantiation time, what the return type of this should be. And then, of course, we do the computation at runtime. So armed with that crazy knowledge, let's go back over here and look at using these min functions. So here you can see we have min 9 and 6. That's obviously going to be an int. And I could also be saying, you know, auto here. Maybe I'll do that, auto here. So this is going to be doubles. We print the results. we'd go ahead and use an explicit cast here. We can't say this. We can't say min of 10 and 11.3 because that version of min requires only one type and they have to be the same. So that won't work. So we have to comment that out. However, we can do an explicit cast here. This says treat the first parameter here as a double, promote it to double. And then down here we have our min ex call, and I'm going to actually show you what type was derived there by using some more type system magic. You can see here I define myself an auto named E, that's the name of the variable, and then down here I say type ID of E, so that'll go figure out the type of E because it's an auto, and then it prints the name, and that'll print the character D, meaning it's a double. And then the final thing we do here is we go ahead and use the 3-parameter version of min to print the results out. So let's go ahead and run this code, and you can see it all compiles, and the results we get back here are minimum of the integers is 6, which is this guy up here. Minimum of the doubles is 10.5, which is correct. And then we do the minimum of, let's get rid of that because that's the duplicative. Now we're going to explicitly promote this thing, which will then return 10. And then down here we use our min ex type deducing, return value type deducing method, which will deduce the type to be a double because it always goes for the higher precision variant. And that ends up being type ID of E.name returns D, because that's how the compiler encodes the type name for a double. So you can see min of D is 10. And then the last thing we do is we get the minimum of these 3 parameters, which of course is going to be 3. So that illustrated a whole bunch of other interesting features with respect to C++ function templates. So now you should be well prepared to do anything that requires function templates in your code for the assignments or other things you may need to do with C++.